Okay. Hello, everyone, again. Let me show you my screen here. So we are on to part 3 of this tutorial. The parts are getting shorter and shorter. Hope you appreciate that. At part 3, I'm just going to show you what COMSOL calls the post-processing tasks, which is really making graphs. And I'm going to show you that right now. So let me minimize this. Let me bring back the COMSOL interface. This is where we left off last time. And COMSOL did make a plot, a surface plot, a little hard to see. And this one's not so bad. So we're actually going to preserve this one because it's not so bad. So it's actually located right at this node. It's a 2D plot of the velocity, and we're going to go to the subnode called slice. So I guess it's a slice plot here. And what makes it hard to see is you are seeing 5 different planes. So if we make this just a single plane, so change the 5 to 1, so we're not seeing 5 different planes. You see, if I rotate it around, it's going to show you we really have 5 different planes we're looking at. That's a little awkward. Change it to 1. Notice these are YZ planes. I could change all that if I wanted to, but change it to 1 plane, and a little easier to see if it's just 1 plane. And we can see the basic characteristics. The inlet is on the right, so let me rotate this around so we can see the inlet a little better. Okay. Probably as good as I can do. So the inlet, you can see that we are starting a little light green here. And that light green is about 2 times 10 to the minus 2 meters per second. And remember, that was our inlet. And you can see that we actually approach a fully developed flow. So remember, we'll be in the red fully developed flow really just within the first 10% of this tube. So we really have the velocity probably a little bit too low here. The entrance length is pretty early in the tube. Now, these heat plots are kind of interesting. People kind of like them. It's a 2-dimensional plot. And it kind of shows the 3rd dimension, which would be velocity as a color. And it's kind of, people always like these things. But you can't read numbers very easily. You have to interpret numbers from the colors. But you can definitely see a couple features that you were supposed to look at in the problem. The inviscid core, which is the green part, it barely sticks in there at all. So the velocity really was way too low. It'd be more interesting to have higher velocities or a fluid of lower viscosity. You see the boundary layer. You certainly see the no-slip condition at the wall because it's blue, and there's always a boundary layer at the wall. But basically, you have fully developed flow. Really, it's only about 10% of the way into the tube you have fully developed flow. So, so I recommend a higher velocity. You see more interesting things. But that doesn't prevent us from making some graphs here. And instead of this kind of graph, I want to make kind of the classic, what I would call a 2-dimensional graph, a YX graph. In COMSOL, it's called a 1D graph. But the velocity versus position somewhere in the tube. And what I want to do is construct some lines within the tube. In the nomenclature of COMSOL, these are called cut lines. And then plot velocity on the cut lines. I'm going to have two cut lines that cut across the diameter, so we can see the velocity profile, and then one cut line that goes down the center line. That's going to be kind of the interesting one, to see how the velocity varies down the center. So I have to construct these cut lines. So let me see how I do it. Cut lines, if I remember right, are in the node called data sets. Let's see if I'm right. Yes, I am. A cut line in three-dimensional space. So I want to select this subnode, cut line in three-dimensional space. So I can locate the line, and so you can see I see, explicitly the node itself. I see the node itself. I probably should have mentioned a long time ago, this center panel is really describes what's in the node that you click on the left-hand panel. Should have mentioned that a long time ago, actually. Okay, so what are we going to do? We can locate a line by 2 points, and I think our first cut line will be down the center. And so the center is going to be, remember that the inlet surface, the center of the inlet surface was at 0, 0, 0, so I can leave point 1 at 0, 0, 0. And I want the other end of that line to be the same xy coordinate, but z is going to be basically the length of the tube. And you might remember I had a variable for that, but I'm just going to put in 0.1 for the length. And that's my cut line. Now I can verify, in case I have any doubt about it, where that cut line is. And so I can plot it, hope this works, plot that cut line and rotate this around. You can see the pink line, I hope. The pink line goes down the center. You can actually see a little better here. Actually, it's a little hard to see, but you can see it. We just created this cut line going down the center. And the idea is we want to, we're going to plot velocity down that cut line. And I want to have some cut lines coming across the diameter so we can see the velocity profile. So I'm going to make 2 more cut lines, and they're going to cut across the diameter at 2 different z locations, just so I can kind of see it a little better. So again, I'm going to right-click on data sets. So right-click, and that's going to be a cut line 3D. And now I want to go across the diameter. So maybe my first cut line will just be slightly inside the tube. So let me say Z. Okay, so the total length is 0.1, so maybe just 0.01, just barely along the axial position, 0.01. And again, after you type something in a box, you've got to either hit enter or click someplace else to have it entered in. So 0.01, so it's just going to be barely inside the box or inside the tube. In fact, I'm going to make this 0.02, 2% of the way in. Okay. And what I'm going to do is I'm going to cut across the diameter in the x direction, keeping y the same. Remember the radius was 0.005, but I can use that as a parameter. Remember I developed the parameter radius, and then I can call this minus radius. I could have also put in 0.005 because that is the radius. The advantage here is that if I do another simulation where I change the radius, this cut line will automatically reposition itself. Okay, so the cut line, if I did this right, point 1, you got the same position in y and the same position at x, but you're at the position radius for x, and point 2, nothing changes with y or x, but you're at minus radius. So we cut across the diameter in the x direction, just to make sure we did it right. Very easy to get mixed up here. Type or hit plot, and there you can see there's our cut line, our second cut line. Okay, it's actually 20% of the way in. I wanted it little. I do want it a little farther back, so let me say 0.5 here. Very easy to get confused here. I want a little closer to the entrance, and yeah, that looks a little better. Pretty close to the entrance. I don't want it to be fully developed yet. Okay, that's our second cut line, and now we'll do one more. The other one's going to be very similar, except just farther inside the tube. So easy way to do that is to copy this cut line. Well, actually, why don't we just construct a new cut line here? Probably could copy it, but cut line 3D, and I'm going to go, x is going to go from radius. Remember, it's radius underline to minus radius underscore. Radius was 0.005. Y is not going to change, but now x, I want it farther inside the tube. So the tube is 0.1, so maybe I want it halfway in the tube. Should be pretty fully developed halfway in the tube. That should be 0.05 unless I'm doing something wrong. Remember, z is the coordinate along the axis. Just to make sure I didn't mess that up, I can hit this plot button, and yes, you can see we're right in the middle of the tube here. That's going to be my cut line. That will be my cut line. Okay. So I'm going to make several plots here. And so go to results, and in the nomenclature of COMSOL, these are going to be called 1D plots. You could argue they're really two-dimensional plot, y versus x, but I guess it means it's one independent variable is going to be plotted, which is going to be x. So let's make a new node, 1D plot, and here's a new node, and I have to tell it that it's going to be the first cut line. Okay. The data set will be the cut line. I think that's all I need to do here. But I have to make a subnode which has details of the graph. So I right-click on this plot, and it's going to be a line graph. So I have to make a subnode called line graph, which has a lot of information in it. And so what do I want to do here? So it's the data comes from the cut line, the first cut line. So change data set to cut line. What am I going to plot? Yes, I am going to plot velocity here. SPF denotes the study here. Where did SPF come from? Yes, the laminar flow. See, laminar flow, SPF, it means it came from this node, SPF, and it's the velocity. But what are my other choices of plotting things? What I can do is pretend like I'm going to replace that. So click on this little funny shaped button here and say I want to do something related with the laminar flow, and maybe it's velocities and pressures, and you can see the nomenclature here. If I wanted to plot the shear rate, the variable is SPF, meaning it came from that laminar flow node, .SR. That's the the symbol that COMSOL uses for the shear rate. If you wanted to plot the vorticity magnitude, it would be SPF vort magna. You can use that as a variable. It's a dependent variable. It's a function of x, y, z. And that's the nomenclature for that COMSOL gives that dependent variable. And this is kind of a handy way to see what the dependent variables are called. Otherwise, you just don't know what they're called. Velocity is kind of obvious. It's a U. It's coming from SPF. And again, you can see here, it's this laminar flow node called SPF. You could change that name if you wanted to, but there's no point to it. But that says that's the velocity calculated by SPF. Again, it's hard to remember that, so you can use this little button here, and you can see how things are named, and you can actually use that variable, like in a boundary condition. Possibly, you want to say, the vorticity is a certain magnitude at a boundary, use that as a boundary condition. You can actually do that. You just have to know what COMSOL calls the vorticity and everything else. You got a lot of, possibilities here. There's pressure, that's just P, that's kind of obvious, and all sorts of other variables here. But we're just going to use, we do want velocity, okay? We want velocity. That's going to be the y-axis. And how about the x-axis? Well, arc length, we actually don't want arc length. We could, it's just hard to interpret, but we want an expression, and the expression is actually x, right? We're going to plot, x, our x-coordinate, remember it goes from radius to minus radius. So we're going to plot x on the x-axis and u, and so let's plot it. Let's see what it looks like. Hope this works here. So plot it, and okay. Wow, what happened here? Velocity magnitude. Oh yeah, we're actually plotting. Yeah, we're plotting down the. We're actually plotting down the center axis. I got this all messed up here. We actually want to, yes, plot the velocity magnitude, but plot it versus z, right? I totally messed up this one. We want to plot it versus z. Okay, a little better here. This is the velocity magnitude versus z. One thing you'll see is it does start at 0.02, and it doesn't quite get up to 0.04. The reason is you need a finer grid to get to that asymptotic value, which would be twice the inlet value. And I did this with a normal grid. I have to switch to a finer grid, and we would get up to that asymptotic value. Well, it looks like it's still climbing, actually, a little bit. So I may have been wrong here. This, it's not really getting to the final velocity. Those colors were deceiving. Not getting quite to the final velocity. Even at 0.1, looks like it's still climbing at the end. Do note the noise here. That's not numerical noise. That's actually a graphical noise, because you may notice that the grid points for the finite element grid, none of those points were exactly at the center line. So if you want to plot something, how it varies on the center line, COMSOL doesn't bother to interpolate between the two nearest, um, nodes in the finite element grid. It just takes the nearest one, and therefore there's going to be some noise. But anyway, it's an interesting plot. This tube was longer. You might get up to 0.039. I still think you need a finer grid to get up to that final 0.04, but that's the kind of thing that you can investigate. But I want to make some other graphs here. I want to make two superimposed graphs of the cross section. That's what I thought I was doing initially. I forgot that that first cut line was down the center line. So let's do it again. Let's make another 1D plot. So go up to Results, right-click, 1D plot group. Okay. And again, I want to do cut line 3D, the second cut line. Okay. I'm leaving everything here at default. You can change things. You can make log scales. You can do all sorts of things, make this graph. I can put labels everywhere. You can make it kind of nice. But remember, I have to make the subnode, which has some of the critical information. It's a line graph. Okay, we are going to plot velocity again. Remember, SPF means it comes from the laminar flow SPF node. And, I could put a title on here. I can make it fancier. But the key thing is the x-axis, not arc length, but an expression. And it won't be velocity again. It's going to be, this time it will be x, because it's what's, I want to plot velocity as a function of x. I'm plotting, now I'm doing what I thought I was doing on that first graph. Cutting across the diameter, how does the velocity vary? I think I have everything set up here. So let me plot it, and there, very interesting. That is quite interesting because it has bumps. May not have expected that. If the velocity slows down near the wall, but at the center it stays, you have this inviscid core where it kind of stays the same velocity. The velocity is going to have to go above the original velocity somewhere, and here you can see it actually did that. This plot might look a little more interesting if I, what I'm actually going to do is superimpose a second graph. So in this plot group, I'm going to put another line graph. That's going to be that second cutting across the diameter. So right-click and line graph. That puts a second line graph. They're going to be superimposed when I get it done. And the second line graph is going to come, I got to say, it comes from cut line 3D. Okay. That's where the data comes from. It's going to be velocity. X-axis, don't want arc length. I could, just a little more awkward graph. But again, X, okay. Notice these two graphs are in the same group, and therefore it's going to superimpose them, and there it did. Okay. Didn't realize if I click someplace else, it plots this. Usually you click up here and make it plot it. But you can see that the center line of the tube, it's starting to get pretty parabolic, almost got to the right velocity. Well, actually not too close. Needs to go up to 0.04, isn't quite there. But you can see two cross sections, kind of interesting. And etc. You can plot pressure down the center line. You can make all kinds of plots. But the line plots are probably the most interesting and useful ones. One more thing I want to tell you is how to export these, the numbers from these graphs into another plot. So for example, on that first line graph, if I right-click on it, you'll see Add Plot Data to Export. So it's going to export this data that's shown here, remember that was the first graph. That might be the most interesting one because it's going up to, starting to get up to, it's touched on 0.039, and it's kind of getting kind of asymptotically getting to that 0.04. But I might want to get those actual numbers in a table so I can examine them. So add plot data to export. So click on that, and you can see under export, here's the plot. And what I can do is, I can export this as a table. It says spreadsheet, but it's really an ASCII table. I can change that. ASCII table. Under advanced, I can change a little bit of the options. But it's going to export this into a graph. I actually have to give it a file name. After I get this set up, give it a file name and say export. It exports it into a text file, but you've got numbers there. That might be better than trying to read something off the graph. You can get numbers, the actual numbers, and you could make your own graph in Excel or something else because you can create a table of numbers. Okay, I think that is the end of part 3. You can see to finish the problem, you just have to do more case studies, different velocities. You can switch from water to other liquids. And the goal is to try to make a correlation, a general correlation for the entrance length, where the centerline velocity divided by the maximum centerline velocity is a parameter. And it can be, 95%, 0.95, 0.9. You're going to have a little bit of trouble if you try to make it 0.99, because that then really, you need a very accurate simulation with a very fine grid. I'm not sure if you're using the VDE system. It looks like you can barely do a normal grid, just barely. You may even have to go back and do a coarse grid. Anyway, I want to stop there for now. And this time, let me make sure I can stop reasonably. Okay, get rid of, sorry about this. I guess I can go here and stop recording.